Okay, the quiz hopefully was fairly straightforward. Find the absolute max and min of f of x equals x cubed minus 3x squared on 0, 4. So you know you're going to have to plug in 0, and you know you're going to have to plug in 4. That's a guarantee. Okay, critical numbers. F prime is 3x squared minus 6x. 3x times x minus 2 equals 0. That gives me x equals 0. I had to plug in 0 anyway. And plug in 2. So I'll be plugging in 0, 2, and 4. F of 0 was 0. F of 2 was negative 4. F of 4 was 16. So this is the lowest. This is the highest. So absolute minimum at 2, negative 4. Absolute max at 4, comma 16. Okay, so that hopefully was pretty straightforward. All right, so that's that. For this coming Friday's quiz, it'll probably be a full curve sketch though. So this was only a very small portion of it. So most likely for Friday, I'll give you a whole graph where you have to do the whole works. Okay, something like from section 4.5. 4.5 is more curve sketching, but you consider intercepts, domain, symmetry, asymptotes, and then the pre-calc stuff, and then all the calc stuff, local max, local min, intervals of increase and decrease, concave up, concave down, and inflection points, and then sketch the whole graph. Okay, I'll talk more about it as the week goes on. Okay. So we are in November, as you know, so we don't have that much longer to go. We have 1, 2, 3, 4, 5, 6 weeks left, and those aren't all even full weeks. Next week we have a holiday for Veterans Day, so it's another one of those. I call it a one-day weekend. And then a couple weeks after that we have Thanksgiving. We have 2 days off. Okay, so we have 6 weeks. Not all of them are 5-day weeks, so we're finishing fairly rapidly. Okay, so we're aiming for the next test, not this Friday, but the Friday after that. That would be the 13th. Okay, please notice we have a holiday on the 11th. So if, a big if, but if everything's according to plan, I'll try to finish all my formal lecture by Tuesday the 10th. Okay, Wednesday's a holiday. Then Thursday, I hope to let you have, question and answer session like I normally do, and then Friday the test. Then after that, we just have one exam left, and then the final exam, and then we're finished. Okay. All right, so that's what's happening now. I was already into 4.4, so hopefully I can finish 4.4 today, the L'Hopital's route, and then I'll start doing a lot more 4.5 stuff, which is more curve sketching. Okay. All right, so here we go. So back to L'Hopital's route. So L'Hopital's route, section 4.4. So if you have a limit of a quotient giving me either 0 over 0 or infinity over infinity, L'Hopital's rule says the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. Okay, that's called L'Hopital's rule. Okay, please note, do not do the quotient rule. It's easier than the quotient rule. Just do the derivative of the top, derivative of the bottom. Okay, so I did a bunch last time. I'll do a bunch more this time. Okay, so I'll start off with problem 33, which requires you to remember how do you do derivatives involving a to the x. Okay, so limit x approaches 0 of x, 3 to the x, over 3 to the x minus 1. Okay, so by direct substitution, put a 0, that's 0. Put a 0 here, 3 to the 0 is 1, 1 minus 1 is 0. Okay, so L'Hopital's rule does apply. So it's equal to, so LHR, what is LHR? L'Hopital's rule. So I differentiate the top, looks like a product. So product rule, right? First, x times the derivative of the second. Derivative of 3 to the x is 3 to the x ln 3, you might recall. Plus second function, 3 to the x, times the derivative of the first. The derivative of x is just 1. All over the derivative of the bottom. The derivative of the bottom is 3 to the x ln 3. Okay, now I plug in 0. 0 times all that is 0, plus 1. So the numerator is 1. Put a 0 there. That's 3 to the 0, which is 1 ln 3. So 1 over ln 3 is my answer. Okay, 41 is kind of an interesting one. Now, you might recall last week, I gave you one L'Hopital's problem where you had to do it twice. You wait until you see what happens to this one. So 41, cosine x minus 1 plus a half x squared divided by x to the fourth. Okay. And I should get that section here, just in case. All right, so if I plug in 0, cosine of 0 is 1 minus 1 is 0, that's 0. So 0 over 0. All right, so L'Hopital's rule applies, take the derivative. So derivative of cosine is negative sine, derivative of negative 1 is 0, derivative of that is x, all over 4x cubed. Okay. And I still get 0 over 0. Plug in 0, sine of 0, 0, 0 plus 0, 0. Do it again. So what's the derivative of negative sine? Negative cosine. Derivative of x is 1. Derivative of the bottom is 12x squared. Still 0 over 0. Cosine of 0 is 1, so negative 1 plus 1 is 0. Plug in 0, that's 0. You do it again. Okay, the derivative of the top is sine x. Derivative of negative cosine is positive sine. Derivative of the bottom is 24x. Okay. Still 0 over 0. Okay. So do it one more time. So it looks like I had to do L'Hopital's rule 1, 2, 3, 4 times. I can tell for sure I don't have to go anymore, because what's the derivative of 24x? 24, and that's not going to be 0 for sure. So this will for sure be the last time I have to do it. So here's an instance where I had to do L'Hopital's rule 1, 2, 3, 4 times until I finally get it. Okay, derivative of sine x is cosine x. Derivative of 24x is 24. Now I can plug in 0. Finally, I get 1 over 24. So you can do L'Hopital's rule as many times as you need to until you get what you need. Okay? So way back at the beginning, overall big picture, 0 over 0. Take the derivative of the top, derivative of the bottom. Still 0 over 0. Do it again. Still 0 over 0. Do it again. Still 0 over 0. Finally, I get something which is not 0 over 0. When I plug in, I get 1 over 24. Okay. So that's that. Okay, problem 43 is an example of a problem where it doesn't look like there's L'Hopital's rule, but you force it. Okay, you force it to be a quotient. Okay, so, where is it? Problem 43. Limit is x approaches infinity of x sine of pi over x. Now, it doesn't look like a fraction. I can only do L'Hopital's rule on a fraction. So what you do is you force it to be a fraction. Okay. So how do you force it to be a fraction? All right, limit is x approaches infinity of x sine of pi over x. Okay, if I'm going to change anything here, I'd rather change the x. I don't want to fool with sine pi over x. So let me just fool with x. Okay, now, multiplying by x is the same as dividing by 1 over x. Right? So I get it to be the way I want it. I need to have L'Hopital's rule. Okay? So do you agree that this is the same as this? Right? Dividing by 1 over x is the same as multiplying by x. If you divide by a fraction, you multiply by the reciprocal, which means you can go the other way. If you multiply by x, you can divide by the reciprocal. Okay? And now I claim this is 0 over 0. See, to do L'Hopital's rule, you have to have a fraction. So I forced there to be a fraction. Okay, now when x gets big, pi over big is 0. Sine of 0 is 0. The bottom is 1 over big. That's also 0. So it is 0 over 0. So L'Hopital's rule applies. Before I take the derivative, let me rewrite each of these as pi x to the negative 1. And this is just x to the negative 1. Okay. If you have a constant on top of a fraction, okay, it's preferred that you don't do the quotient rule. Okay. Bring the x up as pi x to the negative 1. Same thing over here, x to the negative 1. All right, so do L'Hopital's rule. The derivative of the top, derivative of sine pi over x is cosine pi over x. Then by the chain rule times the derivative of the inside, which is negative pi x to the negative 2. Okay. And what's the derivative of the bottom? Negative x to the negative 2. Okay. So that's a negative. That's a negative. It's a double negative, so I made that a plus. X and negative 2's can cancel out. Okay, yeah, you could do the 1 over stuff, but you don't have to. That is exactly the same as that, so they can cancel out. So now I have limit as x approaches infinity of cosine pi over x times pi. Okay. And now that works. Okay, so when x gets super big, pi over big number is practically 0. Cosine of 0 times pi. Cosine of 0 is 1. 1 times pi is pi. So the final answer is just pi. Okay, so the idea behind this problem was you had to force there to be a fraction. You had to force it to be a L'Hopital's group situation. Okay, and I'll do some more of those. Okay, 44 or 45. Okay, x approaches 0, sine of 5x cosecant 3x. Okay, it doesn't look like a fraction, so I have to force it. Okay, and a very nice way to do it is I see a cosecant here, right? So cosecant is the reciprocal of the sine. So sine of 5x over sine of 3x. And there we go. Now, plug in 0 over 0. Okay. Now, a long time ago, we actually were able to do something like this. Okay. We had an identity where we divided top and bottom by 5x, right? We have a sine of 5x over 5x and divide that by 3x over 3x and so on. Okay, but now with L'Hopital's group, it's much faster. Just take the derivative of the top, derivative of the bottom. So the derivative of the top is cosine 5x times 5, chain root. The derivative of the bottom is cosine 3x times 3. Now you can just plug in. So plug in 0. Cosine of 0 is 1 for both the top and the bottom. So I have 5 times 1 over 3 times 1, which is 5/3. And that's exactly what we got way back when we did the trick of divide by 5x, divide by 3x, and so on. Okay, you get the same thing. But now that we're armed with L'Hopital's group, it's a lot faster to do L'Hopital's group. So 5 over 3. Okay. Okay, 47 is another one that's like that. Yeah. Okay, well, this one's pretty there's a natural way to make that into a fraction. There's already a negative exponent there, right? So bring that into the denominator as x cubed over e to the x squared, right? That's very natural. And then I just do that. Okay, that's infinity over infinity, right? You plug in a super big number, that's big, that's big. So L'Hopital's rule applies. Okay, so the derivative of the top is 3x squared. Derivative of the bottom is e to the x squared times 2x by the chain root. And you can cancel one of these x's with one of those x's. So it comes out to be 3x over 2 e to the x squared. Okay. And now if you plug in a super big number, it's still infinity over infinity. So you can do L'Hopital's root one more time. I can tell that I only have to do it one more time because the derivative of the top is just going to be 3. And then, once I have 3, I don't have to worry anymore. So the derivative of the top is 3. Derivative of the bottom is 2 e to the x squared times 2x. Okay. Or 3 over 4x e to the x squared. Okay. And now you can tell that when x gets big, that 4 times big is big. E to the big number squared is big. The denominator is big. 3 divided by big, 0. So the answer is 0 by L'Hopital's rule. Okay. Now, I wasn't going to do something like a 51, but I'll just talk about it. For this one, the best thing to do is get a common denominator and then go from there. Okay. So in other words, multiply this side by ln x over ln x, and multiply this side by x minus 1 over x minus 1, and then go from there. Okay. 53 is pretty much the same thing. Okay. So for 51 and 53, I can go like that, and focus is better. Okay, so get a common denominator and then go from there. Don't have it at subtraction. Force it into just one fraction. Okay, 55 is a little bit different. Let me show you the trick for 55. X minus ln x. So we're going to have to force a fraction in. So this one I'll multiply by x over x. And then I'm going to break this into two. Okay, the limit of a product is the product of the limits. It's a limit of x times the limit of that thing. But that thing now has a fraction. Okay, so limit is x approaches infinity of x times limit is x approaches infinity of x minus ln x over x. Okay, so I'll leave this alone. This one I'll break into two. X divided by x is 1. And then I have ln x over x. Okay, so I'm going to rewrite the whole thing as follows now. I have to go up. I'll leave that alone. I'll write limit as x approaches infinity of 1 minus limit as x approaches infinity of ln x over x. That means it looks like this now. Okay, so I limit as x approaches infinity of x. I leave that alone. This is just going to be 1 minus this thing. So this is all together. Okay, so leave this one alone. Limit as x approaches infinity of 1 is 1. This one is L'Hopital's rule. Infinity over infinity. All right, so this is 1 minus limit as x approaches infinity. Derivative of ln x is 1 over x. Derivative of x is 1. So I have limit as x approaches infinity of x times 1 minus, okay, so this limit is 0. So I have 1 minus 0, which is 1. 1 times big is big, so my answer is infinity. Okay, so again, that's going to be 1, but when x gets big, x gets big. It's kind of redundant. Okay, so that's going to be infinity. Okay. All right, then starting with problem 57, I think it is. You might recall a while ago we did logarithmic differentiation to handle stuff like this. Okay, we have to take logs again here. We will temporarily call this thing y, take the natural log of both sides because, you know, I don't want that exponent floating up there. So we have to bring the exponent down. The way to do that is to take logs of both sides. Okay, so I'll show you how to do 57 through 65. We'll do those kind of problems. Okay, limit as x goes to 0 from the right of x to the radical x. Okay, so how do I do that? Okay, so temporarily call this y. Y equals x raised to the square root of x, which ultimately means I'm trying to find the limit as x approaches 0 from the right of y, right? I'm looking for that, but if I call that y, this is ultimately what I want. There's a reason why you want to write it down also. Okay, it seems obvious now, but it won't be once I get going here. Okay, so one more time. Ultimately, I'm trying to find the limit as x approaches 0 from the right of y, since I now call this thing y. Okay, so I have y equals x to the radical x. Then we play the same trick of taking the natural log of both sides. Ln y equals ln x to the radical x. Bring the radical x down. So ln y equals radical x ln x, which I'm going to choose again. Now that doesn't look like a fraction, so I force it like so. Right? So multiplying by radical x is dividing by 1 over radical x. Okay, so I claim that these two are indeed the same. Multiplying by radical x, dividing by 1 over radical x. Okay. Now I take the limit as x approaches 0 from the right of both sides, so to speak. Okay, if that equals that, they have the same limit. Okay, so think of it as, whoops. Okay, right now I haven't done anything, right? Ln y equals ln x over 1 over radical x. Take the limit as x approaches 0 from the right of both sides. So we're adding to our bag of tricks in Algebra 1. In Algebra 1, right, you had an equal sign. Say, okay, add the same thing to both sides, subtract the same thing on both sides, blah, blah, blah. Okay, now, what are we doing to both sides? We're taking the limit as x approaches 0 from the right of both sides, right, which is legitimate. It takes longer to say all that stuff compared to say, oh, multiply by 2, but you're still doing the same thing. This is the thing that I added to both sides, right? Now, I'm going to work this out, but please notice that's not ultimately what we're looking for. When I work all this junk on the right side, I'm getting the limit as x approaches 0 from the right of ln y. Okay, but way back here, that's the reason why I write it down. I'm finding the limit as x approaches 0 from the right of y. Okay, so I figured out the way to get the limit as x approaches 0 from the right of ln y, and then you can guess what's going to happen after that. How about I get rid of the ln to make it look like that? I have to exponentiate. Okay, so once I figure all this stuff out, I will exponentiate my answer and then get what I want. Okay. So this is going to be infinity over infinity. Okay. When x approaches 0 from the right, you plug in 0.01, 0.001, 0.0001, 0.0001. Natural log drops to negative infinity. You might recall from the graph of natural log. Looks something like this. Okay. So when x approaches 0 coming from the right side, y drops to negative infinity. And how about 1 over 0.0001? That approaches positive infinity. Yeah, square root, but that's still going to be very small. So 1 divided by very small is very large. So this is an infinity over infinity case. Technically, it's negative infinity over positive infinity, but you can do that by L'Hopital's rule. Okay, as long as you have plus or minus infinity on the top, plus or minus infinity on the bottom. Okay, so the derivative of the top is very easy, 1 over x. For the bottom, you have to treat this as x to the negative a half. Okay? Just right here. 1 over radical x is x to the negative half. All right, so by L'Hopital's root, I now have limit as x approaches 0 from the right of 1 over x divided by, okay, so what's the derivative of x to the negative a half? Negative 1/2 x to the negative 3/2. Okay, and now some funny algebra. Now, I'm dividing by a negative a half, which means multiply by negative 2. X to the negative 3/2 on the bottom means x to the positive 3/2 on top. And that x there can slide down below from algebra. Okay, so I slide that x down, that's there, taking inventory here. That x is that x. That x to the negative 3/2 is x to the positive 3/2 there. And dividing by negative half means multiplying by negative 2. So I think we're good over here. And what's that divided by that? X to the 3/2, x to the 1, x to the 1/2, or square root of x. And there we go. So now when x approaches 0 from the right, 0.1, 0.01, 0.001, 0.001, that's close to 0, times a negative 2, which is still 0. Okay, so the limit is 0. The limit as x approaches 0 from the right of ln y. Okay, so I've established that this thing is 0. But that's not what I really want. Okay. That's why I write down limit as x approaches 0 from the right of y. Right now I have ln y. So now I exponentiate both sides. So I rewrite it like this. Limit as x approaches 0 from the right of ln y equals 0. And I put e on both sides to exponentiate. Okay, so that e will cancel that ln. So I have limit as x approaches 0 from the right of y, which is ultimately what I want. The original problem. Limit as x approaches 0 from the right of x raised to the radical x. And the answer is e to the 0, which is 1. Okay, so my answer is finally 1. Okay, so yeah, that was quite involved. Do a lot more of those. I was going to show you 63 and 65. And then I think when I finish that, I'm pretty much done with the section as much as I was going to show you. Let's see. Yeah. In fact, I'm going to mark it off right now. I hope to finish up to 65. Okay, and then after that, we have more curve sketching. And please notice, by the way, for 4.5, 1 to 49, every other odd. To do all the odds is way too long. Even this is already kind of long. Okay, so every other odd means 1, 5, 9, 13, right? 1, skip 3, 5, skip 7, 9, skip 11, and so on. Another way to think of it is start with 1 and keep adding 4s, right? So 1 plus 4 is 5, plus 4 is 9, plus 4 is 13, and so on, right? That's how you can count every other odd. Okay. All right, limit is x plus infinity of x to the 1 over x. So play the same trick. In fact, all of these problems are going to be the same thing. It's just like the one I did. So from, what, 57 through 65, I guess? They're all like that. Call it y, and then you take the ln of both sides, blah, 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 blah. Okay, so let y equal x to the 1 over x. So again, ultimately, I'm trying to find the limit as x approaches infinity of y, right? Since I declared this to be y, I'm trying to find the limit as x approaches infinity of y. All right, so we know the way the game works. Y equals x to the 1 over x. Take the natural log of both sides, ln, ln. So this would be 1 over x, ln x. But if it's going to be 1 over x times ln x, you might as well write it like this. Makes it easier, right? Now, limit as x approaches infinity of ln y. Limit as x approaches infinity of ln x over x. Okay, so that's infinity over infinity. When x gets big, and ln of x also gets big. So I do L'Hopital's rule. Limit as x approaches infinity. Derivative of the top is 1 over x. Derivative of the bottom is 1. And now when x goes to infinity, 1 over x approaches 0. So very similar to the previous problem. Limit as x approaches infinity of ln y is equal to 0. But ultimately, I want the limit as x approaches infinity of y, not ln y. So I exponentiate. E. So again, we have limit as x approaches infinity of y equals the limit as x approaches infinity of x raised to the 1 over x. And we now know that's equal to 1. So that's 1. Okay. All right. Okay, then I was going to show you 65, and that's the last one for this section. And then maybe we can start some curve sketching again. Okay, this one's a little harder. Limit as x approaches 0 from the right of 4x plus 1 raised to the cotangent of x. Oh boy, cotangent of x. All right, so same thing. These all work the same way. Let y be all that stuff. Y equals 4x plus 1 to the cotangent of x. Okay, so ultimately, I want the limit as x approaches 0 from the right of just y, all this. I don't like that cotangent up there, so how do I get it down? Take the natural log of both sides. ln here, ln here. Once I have the ln, cotangent comes down in front. Okay, now I got to force there to be a fraction. So what is cotangent? Cosine over sine. Ln y equals cosine ln for x plus 1 over sine x. Okay. Now I take the limit as x approaches 0 from the right of both sides. Okay, 0, 0, 0. Sine of 0, 0. Top, cosine of 0 is 1, but ln of 1 is 0. So 0 times 1 is 0. So it is 0 over 0. So L'Hopital's rule does apply. Let me get the bottom out of the way. That's easier. Derivative of sine x, cosine x. Derivative of the top, unfortunately, I have to do the product rule. First function, second function. So first times derivative of second. Derivative of ln 4x plus 1 is 1 over 4x plus 1 times 4, chain rule, plus second function, ln 4x plus 1, times the derivative of the first, derivative of cosine x, is negative sine x. Okay. Now, that's very messy, but it doesn't matter. I'm going to plug in now 0. Okay, see, if I plug in 0, I know sine of 0 is 0. That's nice, so that's all gone. Don't even worry about that. Okay, on the bottom, cosine of 0 is 1. Put a 0 there and a 0 there. Cosine of 0 is 1. That's 4 times 0 plus 1 is 1. That's a 4. So it's 1 times 4 plus nothing, all over 1. So it's equal to 4. Okay, so limit as x approaches 0 from the right of ln y is equal to 4. Okay. And you know the way the game works. I found the limit of ln y, 4, but I want the limit of y. So again, exponentiate, put an e here, e here. So the limit as x approaches 0 from the right of y, or the original, is e to the 4th power. So final answer is e to the 4th, is what we're trying to say. Okay. All right, so that's as much as 4.4 as I was going to do. Okay. And 4.5 is back to curve sketching again, but with a little bit more stuff to it that I mentioned last time. So now they want us to consider all of this I talked about before. I mean, it's always a good idea to consider this anyway, but now they're going to give us weirder problems, more strange problems. Okay, so we will consider domain, intercepts, symmetry, asymptotes. Okay, you might say, do I have to memorize this? No, don't memorize it. If you need it during the test, I'll tell you, find blah, 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 find all this stuff. And then the new calculus stuff, intervals of increase and decrease, relative max and min, concavity, points of inflection, and then finally sketch the curve. Okay, so now we can consider all of these things as we work out some curve sketches. Okay. These can get long, no doubt about it. You see, there's a whole bunch. I mean, there's nice problems. It just takes a long time to do a whole bunch. So use these guidelines to sketch the curve. Okay, so a whole bunch of stuff, as you can see. And some more over here. Okay, so I'm going to go make up my own order. I think the polynomials are fairly easy and straightforward. The first few problems are polynomials. Okay, so I was going to jump around and do some of the harder ones. Okay, so I'm going to start off by showing you 21, please. X minus 3 times the square root of x. Okay. X minus 3 times the square root of x. Okay. And I'm going to choose to distribute. It just makes it a little bit nicer. Now we realize that square root of x means x to the 1/2. So I multiplied x times radical x. That's x to the 1 times x to the 1/2. That's x to the 3/2. Okay. It just makes the derivative much easier. Minus 3x to the 1/2. All right, domain. Aha, I got a square root. X is greater than or equal to 0. So the domain is bracket 0, infinity. Right? Intercepts. How do you get 0? Well, 0 gives me 0, and 3 gives me 0. So 0, 0, 3, 0. Symmetry. Well, ordinarily, we would say replace x by negative x, but that's not possible here, right? You cannot plug in the negative of a number, so there's no symmetry. Asymptotes. Do we approach any line? No. When x gets big, y gets big. We know that. So nothing's going to happen over there, right? And so there's no asymptotes either. When x goes infinity, y goes infinity. Okay, so we're ready. Here's my original function. First derivative, 3/2 x to the 1/2 minus 3/2 x to the negative 1/2. Y double prime, 3/4 x to the negative a half plus 3/4 x to the negative 3/2. Okay, now let's rewrite these. Okay, I noticed something for the second derivative. If I write it like this, 3/4 x to the 1/2 plus 3/4 x to the 3/2, right? The negative exponents means put them in the denominator. For values of x which are allowed, which are positive quantities, and 0. Okay, 0 is undefined. If I plug in anything else, this is always positive, right? So the function's concave up from 0 to infinity, for sure. That means it's concave down nowhere, and automatically that means no inflection points. All right, so that makes the graph pretty easy, which I'll get to later. Okay, we can set first derivative equal to 0. So y prime is this. That means square root. That means square root in the denominator. So I'm going to write it as 3/2 radical x minus 3/2 radical x. Okay, so one more time, can't show it to you at the same time maybe. But 3/2, square root is on the bottom. Here square root is on the top. Set it equal to 0. Okay, so I'll add this to both sides. Add 3/2 radical x. It looks like this. Okay. Very conveniently, you can cancel out these. If you multiply both sides by 2/3, they cancel out. And then I cross multiply. Radical x times radical x is x. I get x equals 1. Okay, 1 comma negative 2. How to get the negative 2? I just plugged in. Put a 1 here, square root of 1 is 1. 1 minus 3 is negative 2. Now, I could do a sign chart, but I don't have to. How come? I already know the function's concave up the whole time. So at a critical number, 1, concave up means I have a minimum, U-shaped. So if I draw it U-shaped, it's going to be like that, and I'm done. So I got the graph basically. There's the graph. Minimum, 3, 0, 0, 0, 1, negative 2, which is a minimum. Always concave up. Functions decreasing from 0 to 1, increasing from 1 to infinity. You can't say negative infinity to infinity because it doesn't go that far. It starts right at 0. Okay, so it goes down and it goes up, always concave up. Okay. All right, so that's that. Okay, I was going to jump all the way to problem 41 for you. Let me show you 41 here. This. Go like this. Arctan of e to the x power. So how do you do arctan of e to the x? Okay, so what's the domain? I can plug in anything here. Arctangent, you can take the arctangent of anything. So the domain is all real numbers. Intercepts. Well, plug in 0. E to the 0 is 1. Arctan of 1 is pi over 4. Because the tangent of pi over 4 is 1. So 0 comma pi over 4. By the way, e to the x is always positive. Arctangent of a positive number is positive. So this will never touch the x-axis. Y equals 0 is not possible. Symmetry, there isn't any. F of negative x is arctangent of e to the negative x. That has no relation to this, so there's no symmetry. There actually are asymptotes. When x gets big, x goes to infinity. Arctangent of a super big number is pi over 2. Okay, when x approaches negative infinity, e to a super big negative number is almost 0. Arctangent of 0 is 0. Okay, so y approaches pi over 2 if x goes to infinity. And when x approaches negative infinity, y approaches 0. Okay, so I have two horizontal asymptotes. I'll abbreviate horizontal asymptotes with HA. Horizontal asymptotes. So y equals 0 and y equals pi over 2. Okay. So here we go. Take the derivative. Okay, how do I take the derivative of arctan? You go 1 over 1 plus this thing squared, you might recall. So 1 over 1 plus e to the x squared times e to the x by the chain rule. E to the x over 1 plus e to the 2x. Okay. Something about this expression, you may notice, this thing's always positive. Okay, I wrote that over here. Yeah, I'll get to it, but I have to do the second derivative. You can tell the second derivative is not very nice. Okay, but let me take care of this. Y prime is greater than 0 for all x. Remember, e to anything is positive. So that's positive. That's positive. Positive plus 1 divided by positive plus 1 is positive. Positive divided by positive is positive. This is going to be greater than 0 for all x. So right away, functions increasing from negative infinity to infinity. Functions decreasing nowhere. That means there's no max or min. Okay. What is the second derivative, which is definitely not so nice, right? So bottom times the derivative of the top. Derivative e to the x is itself. Minus the top, e to the x, times the derivative of the bottom. By the way, I cleaned that up to be 1 plus e to the 2x. So the derivative of the bottom is e to the 2x times 2, all over 1 plus e to the 2x quantity squared. Okay, and let's clean that up. Distribute, that's e to the x plus e to the 3x minus 2 e to the 3x. That times that is e to the 3x. And let's see, if I put these two together, I have e to the x minus e to the 3x over 1 plus e to the 2x quantity squared. Okay, so again, I don't need a sign chart for y prime. It's always positive. How about y double prime? Set that equal to 0. Well, when is a fraction equal to 0? When the numerator is 0. So e to the x minus e to the 3x equals 0. Move over the e to the 3x. E to the x equals e to the 3x. Divide both sides by e to the x. This becomes e to the 2x. I don't have any more space for it. That's e to the 2x. That's going to be 1. 1 equals e to the 2x. Take the natural log of both sides. ln of 1 is 0. 0 equals 2x. X equals 0. Okay, and we already have that point. When x is 0, y is pi over 4. Okay, so I do a sign chart analysis for the second derivative. Lay down 0. Okay. And then I pick something on this side, something on this side, like negative 1. Okay. Now, the numerator is the only thing that I have to worry about. The denominator is definitely positive, right? Do you agree? That's going to be positive. So I just have to worry about the top. Negative 1. E to the negative 1 minus e to the negative 3. Okay. E to the negative 1 is bigger than e to the negative 3. So it's positive. You can punch it out if you want. But it's e to the negative 1 minus e to the negative 3. It's 1 over e, 1 over 2.7, 1 over 2.7 cubed. This is smaller, so I subtract positive. Plug in 1. E minus e cubed. negative. 2.7 minus 2.7 cubed. 2.7 cubed wins, it's bigger, so it's negative. Okay, so concave up, concave down. All right, so intervals of concavity, function is concave up from negative infinity to 0, concave down from 0 to infinity, and I have an inflection point at 0 pi over 4. Okay, so quickie graph, and then we're out of time. Okay, so we said this was pi over 2. Here's my inflection point. Always increasing. Okay. On this side, we approach 0. On this side, we approach pi over 2. Starts off concave up, ends up concave down. Always increasing. So here we go. Concave up, concave down. So there's our graph. All right, and that's just about it, folks. We're out of time. Let me see if we got anything in the chat. Or maybe Prasanna got that. So thank you, Prasanna. Let's see. Okay, Prasanna got that. Okay, thank you for. Right, so L'Hopital's rule, either 0 over 0 or infinity over infinity. And we have to force it to be that, if possible. Okay, well, we'll continue with this tomorrow. So tomorrow we'll do more curve sketching and see how it goes from there. All right, that's it for today, folks. So have a good day, and we'll see you later. Okay, bye, everyone.